overall goal is to become experts in quantum dissipation. Everything, all building blocks were prepared for this derivation, to get equations that control how the energy releases how system releases energy and arrives to thermal equilibrium. To be focused a lot on two-level system and good chance to take into account dephasing, so to lose coherency and for Bloch vector to arrive to the center while moving along equatorial plane. We were able to take into account, so it was transversal, we were able to get longitudinal relaxation arriving to thermal equilibrium at infinite temperature for the Bloch vector arriving to the center starting from either north or south, either from the north or south pole, right? And our goal, the remaining 3 meetings, will be targeting a goal to arrive at a situation when we can model arrival of our system to a thermal equilibrium. So the expected outcome of 3 meetings. So I will try to sketch where we should be in whatever 6 hours of derivations and 3 meetings. So we should get the same equation as we already got. So we were able to maybe not prove rigorously mathematically, but to show that the time dependence of the population part of density matrix happens independently on dephasing in some limits. In limits of we are looking at the times longer than coherence time. The problem that we experienced before, that the coefficients in the do not write it, I will erase it in a second. The coefficients in this balanced time-dependent equation, system of equations, were the same. So we were seeing that excited state depopulates and provides yield with the same pace So we should arrive to the rates that are factorized by number of photons in the and please correct me, I will try to reproduce it. It should be I'm always making mistake here. My only way to redirect things. So if you have notes, please muted there. So it should coincide with what we derived last time. But number of photons in the mode of the gas. So this equation, I don't know if you consider it. Hello, Patricia, I see you. Either but consider it nice or maybe ugly, pleasant or boring, but it will be a crown of the whole course. And if you bring us to the detailed balance. What do we see here? So in the limit of 0, first, if you can reproduce in the limit of infinite temperature, number of quanta in the resonance harmonic mode will be infinite, which means
Should be 1 minus E. I think it should be 1 minus E on that expression. Then. Right?
well, I'll put it with different color and then we'll check. So according to one, it should be 1 minus E. Okay. If you have your notes, you can check whether it was correct. But the number of quanta at infinite temperature is infinite, which means the terms here and there will be equal, right? It doesn't matter that they both are infinite. It is important that they're equal. And then we will reproduce the situation that we derived by taking into account random noise, right? Now, the infinity all coefficients are equal. So at least this solution, if you prove that this equation, if you prove that it is correct, it will not violate our previous accomplishments. It will be our previous accomplishments will be a limiting case of this equation. Now, what would happen if temperature is equal to 0? So number of quanta, double check.
Yeah,
0,
no, I think I was backwards there.
Huh?
I was backwards there because it's e to the minus that stuff, right?
So, well, depending on whether we have plus or minus, we can put it on different side. Okay, so t equals 0. This becomes infinity, e to the power infinity into the denominator, which will be 0, 0. This should be plus, right? So I bet it is 1, but I'm still not count on my memory. So time equals 0, number of quanta in the path mode is 0. Then we will have nothing there, just minus constant here, plus constant here. So in the limit of 0 temperature, excited state depopulates with the factor gamma that we will work on for so many hours. And the increment in the ground state will grow with the same rate. So we will have just transition from excited to ground with the space, which means after a certain time, everything will be in the ground, which makes sense. So we will arrive to equilibrium. Ground is 100% populated. And for the intermediate cases, we will have something in between 50% ground and excited populated and everything 100% in the ground. if one would solve this equation in the steady state limit when derivative equals 0, which means it arrives to equilibrium, this equation will provide the detailed balance. So one can get the answer right away. I hate the word detailed balance, but it means that there is a dust on shelves. If one has an empty bookshelf, the one closer to the ground has more dust than at the top, and it obeys Boltzmann distribution. So a little schematic diagram that we started our meeting. So in the center we have Redfield dissipative dynamics. We and our building blocks are rotating frame or interaction picture. The second order independent perturbation theory. The interaction Hamiltonian. The ensemble and thermal state. And density metrics in Liouville space. Right? So it is something we were discussing and preparing to this stage. So from now on, before we were preparing building blocks, and now we are starting to compose them together to get the answer. And the answer will be well, Redfield is something more general, but in the limit of two-level system, it will be what we already discussed. Right? So here is the plan. So I will start as density metrics in Liouville space. Start. Then next we'll try to remember second order derivation theory. Then we'll set up our next steps. I will need to reintroduce or refocus on the ensemble in thermal equilibrium and the concept of brace. So the foundations for our average or ensemble in sense of quantum state. Then I need to revisit the Hamiltonian. And then for convenience of quick answer, we need to do everything in rotating frame, and which means that all operators that we do this will accumulate phase. And then by combining everything together, there will be a transition. So how to go from the second order perturbation theory to equation of motion for density metrics under thermal average. And then after this transition, which I will fail to do in full, at least maybe paving the ways. From here on, we will need to go back from yes, we will take Liouville, return back from Liouville to Hamiltonian, and then do several algebraic steps. So practicing opening commutators and plugging in the Hamiltonian. And basically, this stage is what you are offered to do. So if you have an idea what it is, you can go ahead, or you can wait until we arrive to the same stage together. I'm giving a little disclaimer, and maybe it will be, how to say, a little discouragement or disenchantment, but by the end of today's meeting, we will not arrive to practical equations that can be used to solve application problems. We will arrive to only intermediate stage, like building scaffold. We will have building blocks, building scaffold, but the whole monument needs a little bit more time. So when we will be done with this page, it will be time to stop our meeting. So according to London, wave function can be approximated by getting more and more terms in the perturbation theory, right? If one has infinite order terms and summation, they kind of add back to exponential evolution operator with time ordering. But for practical reasons, most of the times, first and second order are sufficient. The Hamiltonian is unperturbed system plus interaction. Whenever possible, we will you do calculations in the interaction picture, where operators and wave function accumulate phase according to the unperturbed Hamiltonian. So the evolution of density matrix. Please check me on this minus sign. If we are in the interaction picture, then the accumulation of phase is removed, and I believe we spent about 2 meetings, both in lab and on the lecture, to start delivering this. But the main outcome, main positive part of going into interaction picture is that one removes the term responsible for accumulation of phase from the Hamiltonian, and the equation becomes simpler and, in some sense, time independent. Independent or slowly changing. So you do believe in this, or you can prove it, right? I have no doubt in it, but if you're not 100% sure, you can give me a little signal. Is everyone happy with equation of motion? Right? So, what did you learn from Dr. Shaul Mukamal? I believe I was distributing a chart from his book. So that instead of commutator, the rho minus rho v, one can abbreviate it as a Liouville operator. Right? And it is what we were practicing by doing random noise. So we set up density matrix as instead of matrix, we wrote it as a column, and then a super operator as a 4x4 matrix instead of 2x2, right? So you remember this. Okay, so next, so we are done with redefining Liouville. Now, the question is, how would one express what would be the solution for density matrix evolution, density matrix as function of time in the second order perturbation theory for density matrix? So I will write it down as a pure fantasy from the top of the head, and I can make mistakes. So if you find errors, correct me, and then I will check with the cheat sheet. So to get first order, it will be zeros order plus when we were in the Hamiltonian representation, we were carrying out these factors. Now we can hide them inside the Liouville operator. So it will be just integral from 0 to t L of t prime dt prime. So we are taking initial, and if you are in the interaction picture, I shouldn't forget putting this I everywhere. So we start with yeah, we just take initial condition and then we have phase accumulation, which is hidden in the Liouville operator, which is expressed in the interaction picture. Then at a time t prime, we switch from whatever state to whatever state we need, and then we have corrected density matrix. So if we want to get the second order, we need to apply this protocol to the first order. Zeros order. Then not sure about if you really need to start from 0. So I put a little doubt here, but and then instead of zeros order unperturbed density matrix, we need to put here O of t for the first order. If we want to be if we want a general expression to be rigorous, the times that we borrow from here to there should be we should use different absolute values, different indices per time. Otherwise, it will imply that things are happening simultaneously. So here I need to put prime, double prime, and here unperturbed. And again, I'm not sure if I'm putting 0 correctly here. Maybe it should be t. Then dt double prime. After plugging it inside, we will have 3 terms. Picture. Order plus integral 0 t t prime rho of t so what's originating here plus, and there will be a third term that will practice 2 integrals of 0 to t prime 0 t prime integral 0 t double prime L t double prime rho 0 square and times 0 dt1 dt double prime. So when we were practicing a story about random noise, I don't remember if you proved it rigorously or we just admitted it as a matter of belief that if the Liouville operator originating from a resonant harmonic mode with slight fluctuations of the Rabi frequency is centered around zero, and if one performs at some, we haven't performed, but later on, an average over ensemble of the first order term likely will go to zero because of the human laziness. I'm just not going to rewrite this time because we already expected it will be zero. Okay, so we do have perturbation theory for density metrics, time-dependent perturbation theory. I will let it sit here for a bit of time, and we'll offer something on the other board. The quantum treatment of molecules is performed with molecular wave function and molecular Schrödinger equation. Right? So if one has a so big molecule and it has so many electrons, they all are argument of quantum wave function. And at the same time, the molecule has so many ions, right? And it has position of the first ion, second ion, the number of electrons, number of ions. So generally, one can think about wave function of the universe or wave function of a molecule, which is a good concept, but it is not solvable because it's too many independent degrees. In this subject of quantum chemistry that we observe and review as selfish users without going into deepness, there is a so-called Born-Oppenheimer approximation. That tells that with a quite reasonable degree of confidence, one can represent molecular wave function as a product of electronic and nuclear wave function. Electronic depends on electronic degrees of freedom, and nuclear depends on nuclear degrees of freedom. There are additional subchapters and details that electronic wave function may depend on positions of nuclei in a parametric way, slowly changing, but generally this writing is assumed correct. And this is the foundation for basically all pieces of software when one finds electronic structure. So one does some electron correlations and methods like Hartree-Fock, DFT, couple of clusters for electronic degrees of freedom, and assumes that one can do further approximations, thinking that nuclear degrees of freedom are just positions, point charges. So it is a common belief that one can factorize, and I'm not sure if I'm allowed to put a circle with a cross inside. So those who took advanced mathematical recorders can correct me or prompt different symbol. But suppose we want to utilize this idea further in our today's effort in this course. Suppose our primarily interest focuses on electronic degrees of freedom, and we do not care much about nuclear degrees of freedom. But at the same time, we still want to play a game of density matrix. So if wave functions are factorized, then it wouldn't be a big sin to assume that density matrix can be factorized as well. Okay. And as of now, I am exposing myself as a narrow view thinker, pointing only at electronic and nuclear degrees of freedom. In fact, it doesn't need to be necessarily nuclear degrees of freedom. The role of the second, not so important, degrees of freedom can be, instead of this, we can photons degrees of freedom, right? Or in some sense, one can consider pairs of electronic excitations in the systems around our primary system. Pairs of electronic excitations will be bosons, and they may exchange energy through first order transfer. So nature of secondary set of degrees of freedom is quite open. One can do a lot of derivations and conclusions telling that we have primary system. Some people call it just system. Primary system and secondary system, but most common is just telling that it is a path. In case we want to be specific, and instead of language of abstract operators, one can take an example for electronic indices counted by electronic states counted by one index, and maybe it's only one nuclear mode, same as in Jennings-Cummings model, also counted by one index, right? Then if wave function is has one index for C rho, C electron, C path, and we can have index lowercase, index uppercase, and two indices here. So if the wave function is counted by two indices, then density matrix will be counted by how many? 2 plus 4. So n prime, n prime. Right? So here is, I wouldn't say the last, but maybe one of the general and philosophical considerations which is less derivations, more just speaking. So if you do have density matrix with only this limited amount of indices, I just rewrite it n prime and capital. So we may know its equilibrium value, or we may know its time evolution, but generally there are much more indices, right? And it is a quite common formulation of problem that we need only a small part of the bigger system. on one hand. On another, by practical reasons, there is no chance to monitor too many degrees of freedom. So it's kind of necessary to factorize model and identify primary system of interest. And the question is, so if we do have overall density matrix, if you note, I don't know, time equals infinity or arbitrary time, can we reconstruct back? A density matrix that would correspond to electronic degrees only? And I already introduced. It's a little ambiguous because it interferes with pseudo spin, but a lot of literature uses this instead of raw sigma. So n prime. So how to find the quantum state of the electronic degrees of freedom if we do have solution for density matrix of all degrees of freedom? I'm going to say something which I'm confident in, but I don't know how to prove. I will only postulate. If you have a way to put it under doubt, either prove it wrong or prove correct, I will be very welcome to hear that. We all will benefit. So the statement is that in order to get this, so going from larger number of degrees of freedom to smaller number of degrees of freedom uses a word that interferes with chemical process of getting excess of electrons, reduction. But here it is in the sense that we get something smaller. And therefore, this would be called reduced density matrix. So reduced, it doesn't mean that it is an anion. It's just reduced in a sense that it is like contracted, smaller, focused, leaving behind unnecessary details about the whole world. So matrix is expressed as a matrix with indices. Then one would take and perform the trace operation in respect to degrees of freedom of the rest of degrees of freedom that are not of our primary interest. What does this trace operation stand for? Trace of 2x2 matrix is A plus D, so it is summation of diagonal elements. Right? So it is equivalent to summation over n, assuming that we are picking up only main diagonal. Well, with order to function, we will just manually set up indices as to indices A. And I do not have good justification of proof. RDM. I'll take it as a definition. But it is the way to leave behind details of too many unnecessary degrees of freedom. Well, they may be necessary, but they're not. It's not possible to monitor until you have too many quantum computers to predict everything. Right? So, what are we doing in this class? How efforts are organized? In previous couple of meetings, we were following the influence of random noise onto equation of motion for density matrix of our primary system of electronic degrees of freedom. Now, we plan to do something similar. We want to follow just with more bold color. So we are going to follow what would be the consequences onto evolution of the reduced density matrix from more rich dynamics of the complete density matrix of everything. This task is a little silly and useless in case we do know the solution, explicit solution for density matrix of the complete system. If you know density matrix of the complete system, then why should we focus on a little part? And here is the philosophy of the rest of our meetings and this discipline. So after we introduce this operation, we can use all our previous knowledge baggage and derive an equation of motion for reduced density matrix based on our knowledge for the equation of motion for complete density matrix. And then before solving the equation, we will explicitly perform this summation over vast degrees of freedom and then gain additional terms in the equation of motion, which will include perturbations imposed by a path to a primary system. So in some sense, this summation will can be analogous to average over ensemble. So we do summation, and then summation, not explicitly, we do summation for the average density matrix, and then find equations of motion, which include consequences of this summation, right? And then if we are focused on the two-level system, it will be still numerically equivalent to two-level system equation of motion, but it will have an influence of the interaction with many degrees of freedom of other nature, either photons or phonons or excitons, or maybe something else. So this is the main goal and main idea for the remainder of our meetings. And by staying on this path, we will arrive to equations of motion prediction. So equations of motion for density matrix, which will be able to reproduce detailed balance. The only necessity that for both degrees of freedom, we need to keep quantum nature for the both degrees of freedom. So this is a necessary conditions to reproduce detailed balance solutions for the reduced density matrix. So before no one caught me lying, maybe I will catch myself on some errors by watching the recordings, but we've got that density matrix of everything in the interaction picture in the second order, so we have more subscripts than actual information, is unperturbed solution. Plus first order solution that we are going to draw, plus. So our goal is to reformulate this equation for overall global density matrix. Our goal is to convert from solution for global density matrix rho to density matrix view, which will be focused on our reduced, condensed, selected primarily set of degrees of freedom. It's hard to be abstract with our definition of what is our primary degrees of freedom. But we will, to be specific, we will typically consider our primary degrees of freedom as like a couple of electronic levels, and the rest are nuclear oscillations or photons. But it can be more general. So, primary system is trace for vast degrees of freedom or rho O. Which means we are going to put this little race in front of each term. Before going further, we will assume that our system path. So at the initial point of time, before all story started, the system and path density matrices were separate, and we were able to set up initial conditions that say something about their properties before they started interacting. Once again, this letter I here tells that we are focusing on interaction between our system and path. So without this interaction, they would like evolve independently. But this interaction make them to interact, and system changes state of the path changes state of the system. But the word path, there is another, I would say, philosophical concept that so system changes path changes system. If they equal and if they like have equal mass. If a sedan car collides with a train, system doesn't affect path, but path affects the system. So, and it is another assumption that no matter what time evolution is, our path of t is equal to path of time equals 0. So it doesn't change over time. And typically it is assumed in the path times kt divided by statistical sum. If it is in matrix form, then it just gets the projection operator so that it will be diagonal. So density matrix of the path is already in equilibrium, and it is assumed to be so massive so that no events at the system can change the quantum state of the path. So path is already in thermal equilibrium in a sense one practices in statistical thermodynamics, but system is not. So we are looking on influence of equilibrated path on the non-equilibrated system. And this writing, even if I did some little mistakes, it does provide a solution, but it needs evolution from initial time, and the perturbative, if it is only second order, it will accumulate errors very quickly. It gives us good solution only on an infinitesimal increment. We can put all orders of the perturbation theory, but then it will be more theoretical effort than an attempt to give practical answers. So the goal to pursue is to take this perturbational theory expansion as a basis, take this philosophy of thermal path that is not changed by system, and find out an equation of motion for for the reduced density matrix, which will have additional terms originating from trace over path and from the equilibrium state of the path. So it doesn't depend on time; it depends on temperature. So additional terms that affect dynamics of the reduced density matrix. We've done this concept of the rock product and trace, and we need to introduce or revisit linear operators and make sure that we obey the laws of the interaction picture.
Sorry, can I ask?
Yes, yes, please.
I was wondering, you said that the density matrix for your path is constant. I was wondering why is a function of KT now?
If temperature, well, equilibrium, the word equilibrium immediately assumed the concept of temperature. If it is equilibrium and temperature doesn't matter, it means that temperature is zero. And then it is only one limiting case. So our goal is to, in some sense, we are just funneling, projecting, importing thermal equilibrium from the path to the system. If we will correctly derive these equations and then solve the resulting equation of motion for density matrix on the infinite time lengths, or just find its steady state solution, we will reproduce Boltzmann distribution. So the powerful path will bring the system into thermal equilibrium to its temperature. Right? But we do not want to rush to it. We want to see details, how it will arrive there to the equilibrium. Right? And why do we need it? Is the partial answer to the question?
Yeah, so what you're saying is that it's not as if, because from what I heard, it's as if the thermal, the bath is already in equilibrium.
Bath is in the equilibrium, right?
Right.
Which means if it is in equilibrium, we can define a temperature, right? Yes, it was not very well organized and logical by telling about time, and oh, here is the temperature. I understand you're confused.
Is the assumption also that it's not time dependent? Or not enough?
We factorize density metrics of the work onto system and path.
Yeah.
And part of the density metrics factor responsible for the path is assumed time independent and equilibrated. Okay?
Yeah.
Why do we need dynamics? How the primarily degrees of freedom arrive from non-equilibrium excitation to equilibrium? Because if you already know the equilibrium, what's matter? What do we need? A lot of interesting chemical processes, physical processes like reactions or charge transfer in photovoltaics, are exactly happening when one perturbs the system, drives it away from equilibrium, and then it arrives to the equilibrium by making a work, by making putting energy into load. Like for example, the solar cell, if it is in dark, warm room, it is in thermal equilibrium. When we shine light on it, we deviate it from thermal equilibrium. It comes to excited state. And if you bring it back to the darkness, by relaxing from excited state to the ground, it relaxes not on the solar panel, but it goes across through the wiring and does work for us, like runs motors or gives light in the classrooms or powers computers or stuff like that. So the process of returning from non-equilibrium state to equilibrium is a very interesting and beneficial part of both science and industry. We can get a lot of interesting things by following it. But yes, finally everything will equilibrate.
Sorry, one question.
Huh?
Question, sorry.
Go ahead.
I was wondering, at what point were we considering, because initially we were considering density matrix for all the interacting system between this primary system and the path. But here, the one you wrote down is only considering the density matrix for the
I'm just curious where David navigates us. We were able to see the color of the backpack of Adam, but now finally we focus on the discussion. Okay.
So I was wondering, like, here, this is the question that you wrote down. Initially, when you were writing the equation, the density matrix for that B, it was Hall before.
Let's do it. What is
For B, for the bat, it was initially Hall.
Yes. So the actual equation that I want to keep responsibility is only the top line. The rest are little diagrams to communicate the ideas in a more vivid way.
What I'm asking is that at what point did it change to
Just this?
yes, that's the matrix for just the bat? That it was initially sorry.
It should be system as well here.
Yeah.
It was you confused?
Yeah.
So this is not a literal equation. It's just bringing the terms that take into account influence of these factors. Okay?
Sorry.
That's okay. That's okay. Thank you. Thank you. I will do better next year or in 6 years, whatever. This is over. Okay. So the practical goal is to practice this equation. And there are several steps. We will do a little break soon, but I want to finish it soon. We need to do two things. One is very complicated that I will fail. I will just declare it. How to go from this perturbative expansion to the equation of motion. And then after we complete this challenging for me task, the rest will be to return back from Liouvillean to Hamiltonian operator, which means commutators, open these commutators and plug in the explicit expression for Hamiltonian. Yes, I need to finish Hamiltonian and then we'll go to the break. So we can express this interaction of Hamiltonian in two ways. One for photons, then we can follow what we were learning from Hadassah about vector potential and what we had in class about momentum minus charge velocity to m, and then we need to put index for this vector potential and make summation. But this expression can be simply converted into the form of summation over different modes of the resonator or vacuum. Different, and then instead of momentum of the vector and vector field, one can get all strengths of their interaction constant. Then instead of momentum, we can get the let me be simple. Like choose the spin raising moment operators, and then the creation and annihilation operators of the path mode number psi. So this will give us the vector potential. All proportionality constants are counted here, and here we have the transitions between electronic states if you focused on them. So this was for photons. If you're looking for photons, if you look for nuclear degrees of freedom, then we can do the same way. Summation, maybe use letter I capital. Then overlap for electronic orbital state 1. E T R I. Overlap of electronic orbitals as a Kaplan constant. Then the same type of conditions between the electronic states, and then the momentum of the nuclear degrees of freedom I. This non-adiabatic coupling can be derived, and it is it could be mentioned by Lola in her talk, and it is a standard part of the computational chemistry class. And if anyone needs comments about this, I will be very happy to discuss it. Just we do not have time for it, but it is a very pleasant and nice part of the human knowledge, how the nuclear and electronic degrees of freedom interact. I am under circumstances of ambiguity for the reduced density matrix and pseudo-spin operators. So I used to use sigma plus and sigma minus for as operators. And probably if there are minus and plus, it will say that it is operators. And if there are no plus and minus, it will be density matrix. So it's not ideal, but it is something. So system part, vast part. So it could be generally thought like Kaplan constant for even pairs of state, but really for one. And then we have sigma plus sigma minus, and then we have the dagger. So system operators and path operators, they both are linear, and when together it is bilinear. So it's linear in respect to each other. So if we expressing everything in the interaction picture, it means that P psi of T will accumulate phase. So it will be B psi at time 0, E minus I omega psi T. Same conjugated B dagger psi of T will be E plus I omega psi T, E psi dagger. And for raising and lowering operators for pseudo spin, it's the same story. So sigma minus of T will be E to the minus. Then we need to say just delta. Yeah, let's call it delta T sigma plus I delta T sigma plus. So if we are in the interaction picture, the Hamiltonian needs to be expressed in this in rotating representation. So we are working in the closed near resonance limit. So we are assuming that all modes of this oscillation so vast are approximately equal to delta. And then there are several terms where these two frequencies add together. So they give little, including these terms, will give little correction to the answer. But generally, it's like less than 5%. So those terms that move in the same direction can be dropped without loss of any significant information. And in the remaining terms, the expressions that are very close to each other, they are subtracted. Right? So here we have E I delta minus omega xi, which is very close to 0. And here we have E to the power minus I delta minus omega xi times t. So this frequency is very close to 0. So it's almost time-independent terms. Okay, let's do a 5 minutes break, and then I'll continue whatever I can. So I'm skipping an important step, but there are very beautiful and elegant abstract mathematical derivation, a couple of steps that are the core of the whole thing. I'm sorry to skip it, and I'll just point the steps. So the stuff that we wrote here, let's just count amount and names of objects. So we used to have three times, right? 0 t prime t double prime. And we used to have two integrals, right? In the expression here, we have different instants of time, 3 of them. 1, 2, 3, and 2 integrals, first and second. This was an evolution of density metrics from the past to the future. Right? So it's a perturbative expansion of the evolution operator. One can write it down as e to the power 1 plus first plus second order as in Taylor expansion. But we do need not the evolution at any time, because then we would need evolution operator of infinite order of perturbation. We need just infinitesimal increment. We need time derivative, right? So here, maybe it's not, and this is not the whole derivation. I'm just doing this kindergarten kids by painting pre-made sketch. So evolution at time t can be obtained from state of the system at initial by applying evolution operator, right? We agree. Now, if we apply time derivative, initial condition is not changing. So time derivative is applied only to evolution operator. But it doesn't help us. We need to generate local in time local differential equation, so that we need to apply time some form of differential or some form of operator to density metrics at time t. So instead of 0, we need a row of t here. And why not? We can take row of t and propagate backwards in time. Right? So we just replace initial condition can be achieved by taking our present and traveling backwards with the time machine. Right? So here is our time machine. And then we remember it is a previous line. We are applying, in order to get derivative, we just multiply this initial condition by by the time derivative of the evolution operator. So time derivative of evolution operator times inverse of the evolution operator. In some sense, you can say that it is a Redfield operator. So we are getting the differential equation, time increment of density operator equals to density operator multiplied by some super operator, which is expressed this way. Okay? It's not the whole story. It's another 2 pages of derivation between this equation and the next that we are going to do. But if we imagine that we are applying time derivative to this expression, or doing this elegant stuff, taking time derivative is inverse to integration. Right? So if you perform derivative, it will be 1 less integral and 1 less time instance. So therefore, I'm just inviting you to believe me, which you do not need to, that if you need time derivative of the reduced density matrix, which is just this stuff, we can get, so we one time derivative. It will sound maybe convincing, but it is not mathematically rigorous. So dt and integral times d tau do the same way as the figure that Adam practiced and taught us before. I do not know which imaginary characters they are, like, I don't know, dragon and the butterfly, but same as the snake and the rabbit. So they disappear. They both disappear. So we write down an equation of motions. We write on the left. We have a time derivative. On the right, we did apply time derivative, but we do not have it anymore because there were integration. And integration and differentiation as opposite operations, they canceled each other. I'm trying to be convincing, but it is not the whole story. If one wants to do it rigorously, it's few more very elegant steps, but not in this time frame. So we are going just with this equation. I double checked with my notes that, and I just want to follow them so that I myself will not be confused. Instead of 0, I put time initial t sub I. We start from certain initial time, which can be 0, minus infinity, or whatever. And now we do have path density matrix at initial time, and basically it's not going to change much at all. And the system density matrix at time t prime. Before we had performed this trace operation, we used different notations for reduced and initial density matrix. But later on, we will come back to a definition that the right part of the equation will include the same sigma as the left. So what we have to do, we need to recall the way how we defined the Liouville operator. I know that it is a blind spot, but it is only for us, not for those who are viewing it in the report. So minus I storage bar, comma rho equals L. So now we need to come back to regular life of simple guys and return from this exotic Liouville operator to just regular interaction Hamiltonian. So I'm going to arrange the information of this equation and just continue with things. sigma T equals this. Integral prime. So we need to maybe treat first instance of Liouville operator acting on this system and bus operator. There is one more trick that I'm going to practice. If we would not admit thermal equilibrium of the bath, if the bath density matrix will still serve as a quantum operator, we would need to carefully keep commutation relations in respect to bath density matrix. But since we assume it's equilibrium, right? So it's diagonal, it's same like identity operator with just some values. It loses its commutation nature and it can be safely moved across commutations and kept all the time at the end of the expression. And if needed, it can be proved. So I will carefully process commutation related to this Liouvillean and to system density matrix. But the bath density matrix will always stay to the far left, and it is permitted in these circumstances because we assume that it is in a thermal equilibrium. Okay. Slowly but surely. T prime. I keep this L of T prime, and then replacing this combination as minus I H bar V rho S T prime V of T rho of T prime. The major challenge is to keep track of times. It is my potential for failure. Minus rho S T prime V of T. You're okay with this, right? You didn't catch me lying yet. Okay. I'm going to put a dummy line where I will not do any derivations. I will just rewrite things to ease the next step. D, G, C, G, trace, E, E, G prime, L, G prime. I can put minus IH bar front. E, C, O, prime. L, prime. Rho, S, T, prime. V of T, close bracket, and here we have rho path initial time. So we are halfway through. Right now, we need to do a little more of abstract exercise and assume that this Liouvillean operator acts on whatever it does see after it. Next, right? So by rolling it backwards from Liouvillean to Hamiltonian way of dealing with quantum mechanics, you will get another I or H bar, right? Squared is E. Here, opening the first term. So it will be V of T prime. Here. T rho S T prime minus E T. And then take in the interaction Hamiltonian originating from Liouvillean. V of T prime. Maybe to save space, I will just do it in 2 lines. Now here I have minus V of T prime times minus plus, right? So 1 minus is from first commutator, second from the second commutator, and together they give plus. So I'm repeating this thing, rho S T prime V T, then V of T prime. And at the end, we have the CHEM matrix at initial time for the path. Right. So can we cancel or subtract anything? Taking into account that all these objects are quantum operators, their order does matter, and it looks like there is no repeating patterns. So first and last have operators first density matrix second, last has density matrix first operator second, and the midterms do have density matrix in the middle and operators to the left and to the right, but they are expressed at different times. So nothing can be cancelled at this point. We need all 4 terms. Okay, so now the plan is as follows. We will plug in the explicit expression for interaction Hamiltonian, which we do have on the other board. And then you will see that it is, we experience a little order of human abilities or word availabilities. So we would need to like use the Hamiltonian 1, 2, 3, 4, 5, 6, 7, 8 times, and each of them is quite bulky. Okay? Try to place the terms of maybe put anything possible outside of the bracket, and then just redistribute the part that you need be in here inside this expression. This will be the last part to do today. It is in your quizzes. If you already have an idea, you can do it on your own. I will try to do it on the board and maybe ask for the volunteers to come and contribute. So as soon as we will perform this operation, as soon as we will plug in the expressions, there will be, I wouldn't say nothing, there will be still several steps, but we will see the light at the end of the tunnel. So it will be a way to get to the equation of motion for the reduced density matrix. But now you see why we split this effort over several meetings. So just writing one more step will take the whole remaining time. Why cannot we use just v squared? Yes. And if the explicit with this times, they will be added or subtracted. So it will be different patterns of accumulating quantum phase. Before we dive into this ocean of terrible equations, what do we expect? Like, how do we connect the expression here and our final set of equations that were declared at the beginning of the meeting? Like, we're getting to get something really scary and lengthy, right? And at the beginning, we considered just two differential equations for populations of ground and excited. Do we see any connections? Do we see any light at the end of the tunnel and at least hypothetical roadmap? Would you please focus on Adam? I know you would like to. I just delay time to write an equation. So let's discuss which connections do you see?
I couldn't.
What were the factors in front of the equation of motion at the beginning?
N.
Yes.
Yeah.
And what is M?
Is 1 over exponential of.
Okay, this is correct. Yeah. But just to have a diversity of opinion, London, what is expectation value of N?
Please focus on the number of photons in our bath.
This is correct. And in terms of creation and annihilation operators?
That would be creation, annihilation.
Yes, this is great. Tori, do you see any connection between what is written on the bottom of your notes and pair of creation and annihilation operators?
Now about that, I see a connection between of d prime and just v of d. So we have the same equations, but one implied d sub.
Okay. Patricia, any comments? No, you do. So what is N?
Number of quantum.
Yes. And now look on the other board. What Hamiltonian consists of?
What M2 consists of?
Yes.
Of number of quanta?
Yeah. Hamiltonian consists of creation and annihilation operators. So V includes creation and annihilation operators linearly. But if you do have V times V, would it have product of creation and annihilation operators? Do you see connection?
Yes.
Okay, yeah, thank you. David, sorry that all questions were answered. I hope you don't mind. So here is the Hamiltonian that we are going to plug in, right? And it does include this P psi, right? So after we do V times V, it will include terms like B dagger B. And after we perform an average over trace over bus states, it will give us number one. Okay. Of course, there are like indices and all this suffering of taking account of too many terms, but you see the principle. So Hamiltonian interaction Hamiltonian will come into the second order, and then linear creation of initiation operators of the path will come into second power and will give number of quanta. And number of quanta depends on temperature, and if you factorize to transitions emission excitation with different intensities. And if you be our path towards detailed balance. So I think I can we did agree to erase this one and this one. So I need to keep only this equation as our integral, and the rest can be erased from this board. So after we practice rotating wave approximation, we keep only counter rotating term. We have plus and minus, and plus and no sign, like only rotating in the opposite directions. Right? And then we can carefully write down this phase factors. So do the last step on this this projector facility. So, well, even if it is not recorded, most of us are here. So let's try doing it together. So I do have stickers, right? And we can just, one of us can come and place one or two stickers. Oh, yeah, one or two. If everyone does two stickers, then someone will be unemployed. So the stickers, I was doing it a couple of years ago, and notations are slightly different. So the instead of psi, it is K, and instead of delta and omega, it's delta and nu. But what we should care only about, other than that, left and right forms are identical. The only difference is that they are evaluated at time t and time t prime. Right? So basically, we need to look into this board or whether we do have the interaction of Hamiltonian evaluated at time t or t prime, and then go ahead and paste the sticker. So because here it was a little bigger piece of paper, but I put a t prime in here. Patricia, would you like to be the next? Yes. So it's time t. A. Yeah. Stephen, would you like to come and try it right away? Okay, thank you, Patricia. So here is the game that we play. We look at this key. So we have a construction, and we see whether it is T or T prime in a box. And then we select a sticker and put it in into the right spot. So this is when it is T prime. Guess where to place it. So just use this key on the board. Yes. Yeah, thank you.
That's where I came down.
Sorry? Here is one without prime, if you want. Hello? This is also without, just T without prime. See, let's include this T prime out. Next. Thank you. So when this prime, that should go. Okay. This is a very complicated task. That's perfect. That's perfect. Thank you. So many thanks to all of you for these contributions. I would fail to write it with so high speed on at the board. So what we are missing, what I didn't put here in this quiz, we can assume that summation over all possible degrees of freedom and complex constant are hidden in the trace, or it would be probably safer to write down the summation over coupling constants up front. Summation, well, it is okay here, and then it should be sub P. So it would be too much for now to complete this, but we will continue in a week from now, next Tuesday. And as you have recognized, the goal is to identify the combinations of like B and B dagger will give n+1, which is emission, and combinations of B dagger and B will give n, which will be absorption. Okay, so meeting is done. Everyone is welcome to disconnect and depart. I think we're getting kicked out of the room for the next class.